A rational function is a function that is a quotient of two polynomials where p of x and q of x are both polynomials, and the denominator, q of x, cannot be equal to 0. Basically, a rational function is going to be an algebraic expression that is a fraction and has at least one x in the denominator. Because of that variable in the denominator, there are going to be excluded values from the domain because there's going to be a place where that denominator is going to equal 0, and that can't happen. So when we write the domain of these type of functions, we're going to have those unions because we're going to have one interval where the graph exists, and then it's going to take a pause, and then another interval where the graph continues to exist. Now this information up here is all about the actual parent function for a rational function in the form of f of x equals 1 over x, which has the domain that goes from negative infinity up to 0, but does not include 0 and continues on to infinity, and a range that does the same thing. So we actually have a vertical asymptote and a horizontal asymptote, which leads me to asymptotes. An asymptote is a boundary that a function can approach but not touch or cross. Most of the time, these are going to be linear boundaries, so we're going to be able to solve for their equation of the line that the particular rational function does not touch. Now, horizontal and slant or oblique asymptotes are actually end behavior asymptotes. So the graph could possibly touch or cross those end behavior asymptotes in the middle of the function, but they wouldn't towards the end of the domain because, as I mentioned, those are called end behavior asymptotes. Now for today's concept, we're going to be focusing on those excluded values from the domain. So we're going to be focusing on finding vertical asymptotes and removable discontinuities or holes in the graph. Now these holes in the graph are called removable discontinuities because we get them by canceling a common factor, and when we cancel that common factor, we remove that excluded value, sort of. Both our vertical asymptotes and our removable discontinuities are going to come from the denominator, but the vertical asymptote is going to come from a simplified denominator, and the removable discontinuities are found by simplifying the denominator when we cancel out any common factors. So let's take a look now at these examples. Of course, the first thing that we're going to want to do is to factor both the numerator and the denominator and simplify if possible. For the numerator, there are no common factors between 2x and negative 11, so that just stays 2x minus 11, but the quadratic denominator, x squared plus 2x minus 8, factors into x minus 2 times x plus 4, because positive 4 and negative 2 are the factors that multiply together to give us negative 8, and that add together to give us positive 2. Since there are no common factors in the numerator and the denominator, we have no removable discontinuities, and we have two vertical asymptotes, one of which is located at x equals 2 and the other at x equals negative 4. So for example 1, we have a domain that goes from negative infinity up to negative 4 but skips negative 4, and goes to 2 and then skips 2 and continues on to infinity based on those vertical asymptotes being located at positive 2 and negative 4, and we have no holes. Now let's take a look at example 2. So just like this last time, the first thing that we need to do is factor the numerator and the denominator. Both the numerator and the denominator had a common factor of x that I was able to factor out, and now the denominator is still factorable. Since we're able to cancel out the common x, that is going to give us a removable discontinuity at x equals 0, and then we have two vertical asymptotes, one at x equals 1 and the other at x equals negative 1. Now with 3 values excluded from our domain, we're actually going to have 4 intervals in the interval notation. So I listed the domain as excluded value of x as well as the interval notation so you could see the connection there. For example 3, we're going to do the same process. Factor both the numerator and the denominator, look for any common factors, and determine the vertical asymptotes and removable discontinuities if there are any. On the domain on this one, I did go ahead and list it out in that super precise set builder notation that says all x's such that x is an element of the set of all real numbers and x cannot be equal to negative root 5, 0, and root 5. Now we're going to take a look at the examples on the back. With these examples on the back, we are going to be able to see the connection between these excluded values of the domain and the graph because we're given both the function equation and the graph. So number 4 is already simplified. There are no common factors, so we have a vertical asymptote at x equals 0 and no removable discontinuities. And then we'll have example 5. Just by looking at the graph here, I can see that I should have 2 vertical asymptotes, and since my denominator is quadratic, theoretically I shouldn't have any common factors in the numerator and the denominator, therefore no removable discontinuities. Now let's take a look at example 6. I have no common factors in the numerator and the denominator, and I clearly have a vertical asymptote on the graph with just a linear denominator. So that just reinforces for me that I don't have any removable discontinuities on this graph. Example 7 looks like we're going to have 2 vertical asymptotes and we have a quadratic denominator, so it's likely that we won't have any removable discontinuities on this one either. I also want to point out to you guys at this time that our solutions or our zeros on the graph are going to come from the factor numerator. So once we factor that numerator, we'll see the factors that generate the solutions -3 and +1. And example 8, our last one on these notes. We don't have any common factors in the numerator and the denominator, so we're not going to have any removable discontinuities, but we do have a vertical asymptote at x equals -1. So that is it for today's notes. To review, in order to find the excluded values of the domain, we're going to be focusing on that denominator of the rational function. The vertical asymptotes are going to come from the simplified denominator, and any holes in the graph or removable discontinuities are going to be found by any canceled common factors that we removed from the equation. We'll talk more about zeros of the functions as well as horizontal and oblique or end behavior asymptotes in the next lesson.